Okay, so in this video, I'm going to go through the answers to 2012, question 2, which is the one that has this equation in it that has the Cx and Hy at the top of it. All right. And the first question, A, is calculate the number of moles of the hydrocarbon in the vessel. So you want to look for that one. I didn't bring home the actual questions. All I brought home were the answers. So what I want to go through is, I think question A is fairly straightforward because all you had to do was calculate the number of moles based on PV equals nRT. And then question B, you just had to subtract the number of moles that you were given, the ATMs that you were given from the ATMs that you the total ATM. So that's just Dalton's law. We went over that in class. Okay, the next one, C, is the one that I'm going to go over. So the partial pressures are at 127, which is 400 Kelvin. And after the reaction, you get 600 ATM for CO2, 0.6 ATM for CO2, and 0.8 ATM for water. So what I did was the way that we would have done this problem, the way we would have learned it, that's what I did. All right. So here's the reaction. All right. Let me see if I can make that a little better. Yes. Okay. So here's the reaction that you're given. Before the reaction, you were given 0.2 ATM for the CXHY hydrocarbon, and then you combusted it with 1.2 ATM of oxygen. They tell you in the problem that the oxygen is excess by saying that the last statement, if you read the problem, the last statement is there's O2 remaining in the container. And so therefore you know that this is excess. But after the reaction, there's 0.6 ATM of carbon dioxide and 0.8 ATM water. So the question really is how many moles or what pressure. They want to know what is the pressure of the O2 that's consumed. But what we are going to have to figure out is how many moles are consumed. Because in my classroom, we really do a lot of stoichiometry. So since we know these two, and we can, using stoichiometry, find out how many moles of oxygen there are in this, then using that, we can use PV equals nRT to find out the pressure of the oxygen that was consumed. So follow me here. I took the moles of the water and found out, I took the pressure of the water, the 0.8, and found out how many moles of water that was. Then, using the moles of water, I found out how many moles of O2 that would have. So how many moles of O2 did it take to make that many moles of water? Then I took the pressure of the CO2, I plugged it in, and I found out how many moles of CO2 that is. Then, using stoichiometry, I found out how many moles of O2 it would take to make that much CO2. So imagine if I was just making, in another equation, a totally different reaction, that many moles of CO2, what would my stoichiometry be on the reactant side to make that many moles of CO2? Okay? So now I know that to make this many moles of CO2 and this many moles of water on that side of the reaction, I'm going to have to consume this many moles of O2. So that's how many moles of O2 came from the reactant side. Now remember, there's excess. So there's still going to be O2 on the other side. So I took this many moles of O2 that was consumed and I plugged it into PV equals nRT, and that was the pressure of the O2 that was consumed. Now, we don't know what the initial pressure of the oxygen was because we don't know how much oxygen there was to start. There could be a huge amount left over. They're not asking us that. They're only asking us how many moles were consumed so that we can figure out the pressure of what was consumed. And the way that we would solve this in our class is to take those pressures, turn them into moles, and then use stoichiometry. Okay? All right, now we're going to look at the next problem. The next problem wants us to find the coefficients for that equation. Hang on. Okay, on the basis of your answers above, write the balanced equation for the combustion reaction and determine the formula of the hydrocarbon. So, okay. So here's our formula. Notice no coefficients in the x and the y. So what I did was I plugged in all of the pressures that we know. Now, remember, like at first, it might look like, yeah, but that wasn't the pressure of the oxygen in the beginning, so that doesn't make any sense. But remember, the oxygen pressure in the beginning was excess. And so the balanced equation would not include the excess because let's say there's 3 moles of oxygen remaining and it's got its own pressure. We don't care about that. The balanced equation is only the recipe that makes the equation work. If we have leftover oxygen, that is not involved in the actual equation. So when it says 1 atm of oxygen was consumed, that's all we care about. All right, so we have all these ATMs. Now, remember ideal gases, because 1 mole at STP is equal to 22.4 liters, that means that no matter what the gases are, if the pressure remains the same and all the gases are in the same tank, we don't have to worry about anything because we could do PV equals nRT on all of these in the same way, and the pressures are relative to the moles. So, because they all react the same way, volume, pressure, and temperature-wise. So therefore, pressures and volumes are equivalent, and moles too. So remember, the mole fraction equals the pressure fraction. Well, what we're going to do is we're going to transfer these pressures into moles. We're going to transfer these pressures right into moles. So I'm going to find the whole, because the pressure fraction equals the mole fraction, right? So I'm going to find the whole number ratio. I'm going to divide by the smallest number, which is 0.2. Now that gives me stoichiometry of 1 to 5 to 3 to 4. So that gives me the coefficients of the equation. And I can do that with pressures. I could do it with volumes. I can do it with anything. As long as the pressure in the, stays the same and the temperature stays the same, I can do it with pressure or volume. But now I need to get my x and my y. So balancing wise, since I have my coefficients, I see that there are only 3 carbons on my product side, which means my x has to be a 3. And I see that I only have 8 hydrogens. They're only in one place. So my y must be an 8. So my final equation is here. Now remember, this is the kind of problem that you're just going to pick apart. All right, you're just going to pick it apart. But remember, pressures and volumes and moles are all connected when it comes to gases as long as the temperatures and the moles don't change. Okay, as long as everything stays the same, you can just manipulate all of these. All right, so the next video is going to be on the 2015 test, so you can get that out.